Hello everyone, welcome back to another video. Today we are going to be deriving an expression to find the volumetric flow rate in a rotameter based on the height of a ball. So basically what a rotameter is you are going to have this cylinder that is going to have a slight outward slope on the outer perimeter right here. As you can see, it is going to be starting out with an initial diameter down here, and it's slowly going to be expanding outwards to this diameter up here at the top. This is going to be a wider diameter than this diameter down here. And basically what's going to be happening is there's going to be a fluid down here that is going to be pushing up, trying to climb up the rotameter, and as it's pushing up, it is going to carry this ball up with it. So as you can see here, we have this ball. Now this ball is also going to have a diameter of DO right here. So we'll go ahead and write that out. This length is going to be DO because at the start when you have no fluid flowing up through it, this ball is going to be all the way down at the bottom, and it is going to keep sinking until its diameter is equal to the diameter of the ball itself, because then it'll be stuck against the walls and it can't go down any further. So this DO is going to be the same, the diameter of the ball is going to be the same as our initial diameter down here at the bottom. Alright, so now that we know a little bit about what's going on in this situation, we can go ahead and write out some of our vectors. So obviously, this ball is going to have a force of gravity acting down on it that we will call Fg. Obviously, the gravity is going to be pulling it back down to Earth, so we're going to use Fg to represent that force. And then this ball is also going to be having a buoyant force on it because it's going to be floating on top of that water. It's going to be pushing it up, so we'll call that Fb, right? And then we'll go ahead and draw out what our water is going to be doing, or not necessarily our water, but our fluid that's going to be within our rotameter. We'll go ahead and use a different colored marker to represent that. So this water is going to be starting at the bottom down here. It's going to be climbing its way up. Then it's going to be getting pushed to the outside of this ball, right? It can go either way. It's going to be going all the way around this. It doesn't necessarily have to be in this specific direction. But it's going to be pushing itself up, and it's going to be getting enclosed in it because it's got a smaller area to go through than it does down here. And then it's going to get around the ball, and it's going to be expanding back out. And then it's just going to continue on up. So that is going to be the path that our fluid is going to take. And obviously, this ball is going to be having a pressure force acting on the ball. The fluid is going to be wanting to climb up through. That's going to be creating a pressure force that we will call FP1, pushing the ball up. So we'll go ahead and write that out over here because we're kind of running out of room within our cylinder. So we're going to have FP1, which is our pressure force from below the ball acting upwards on the ball. And then once this fluid is up here above the ball, it's going to be pushing back down on the ball, creating a second pressure force that's going to be acting downwards on the ball. So we can go ahead and we will call this FP3 because there's three areas that we're going to be looking at down here below the ball. That is going to be, area 1, and then over here, once the area that the fluid is going through gets constricted due to the ball, that is going to be area 2. And then we'll have it once the fluid expands back out, once it gets above the ball, it's going to be area 3 that we're going to be looking at. And the pressure force has to do with area 3 once the fluid gets above the ball and starts pushing back down on it. All right. And then down here at the bottom and down here at the top, those are going to have their own volumetric flow rates that are going to have their own velocity of the fluid and then the area that the fluid is going through. So that is going to have its own area 1 and velocity 1 down here at the bottom below. And then once it gets constricted over here to the sides, that is going to have a separate area and velocity through which the fluid is going to be acting. So that's going to have an A2 and a V2, like so. And there you go. That is going to be all of the vectors. Not really sure if you can see it. We'll go ahead and try to pull the screen closer. Probably should have drew this up a little bit bigger. Make sure you guys can see. Alright, now we've got all our vectors written out. So the first step when trying to create an expression for the volumetric flow rate relating to the height of the ball within our rotatometer is we're going to want to find the effective weight for our ball right here. And that equation is going to be the density of the ball minus the density of the fluid. That's going to be the first part of it. So we'll go ahead and write that out. So this is going to be our density of the ball minus the density of the fluid. And then that is all going to be multiplied by the volume of our ball over here, which is going to be 4/3 pi r cubed. And you see we're given the diameter of the ball over here, our DO, which is going to be the initial diameter within our rotatometer. So we're going to have to find an expression for this radius in terms of the diameter. And we know that 1/2 of the diameter is just going to be equal to the radius right here, right? So what we can do is we can cube both sides so that we can put this expression in for r over here. So what happens when you do 1/2 dO cubed? This 1/2 is going to turn into a 1/8, and this dO is going to get cubed. So r cubed would equal 1/8 dO cubed. We can go ahead and substitute this in over here. And what's going to happen is this 4/3 is going to be multiplied by 1/8, or 1/8, which is going to turn into 4/24, or 1/6. So what we can do here is we can erase that out. We're going to put 1/6. And then this is going to become dO cubed right here. Go ahead and erase all that. Alright, and then we are also going to need to add on our acceleration due to gravity at the end over here. That's an important part. Can't forget about the acceleration due to gravity. And then we are going to set this equal over here to our pressure forces multiplied by the area of our ball over here. And what we are going to say is that our P1 force acting up on the ball, that is going to be the positive direction, and this P3 acting down on it, that's going to be the negative direction. So we're going to put P1 minus P3 over here, and then that is going to be multiplied by the area of the ball. Alright, our next step is going to be multiplying this side by the area of the circle. So that is just going to be pi r squared, which again, we do not have an expression. We are not going to know what the radius of the circle is. We are only going to be given the diameter. So we're going to have to substitute an expression for the diameter. And once again, we know that 1/2 the diameter of the ball is going to be equal to the radius. So when you square both sides, you're going to get 1/4 dO squared equals r squared. Go ahead and substitute that in for r squared over here. So this is going to become dO squared over 4. There you go. Go ahead and erase this right here. Alright, and now we can go ahead and do some algebra and cancel some things out right here. We have dO cubed on this side and dO squared. So we can cancel out that dO squared, cancel out that exponent, so we're just left with dO on this side. Then we can multiply this 4 over to the other side. This will turn this into a 2/3 right there. And yeah, we'll pretty much just put this P1 minus P3 on one side and multiply this 4 over. So we'll go ahead and do that now. Also, these pi's are going to cancel. Almost forgot to mention that. That's important right there. So this is going to turn into P1 minus P3 is equal to the density of the ball minus the density of the fluid. Then this is going to become a 2/3, so this is going to be 2 diameter of the ball multiplied by the acceleration due to gravity, and this is going to be all over 3. And there we go, we have an expression right here. And there is going to be a sudden expansion right here when we go from our second zone of the problem to our third zone, when the fluid starts expanding out after it gets the ball. And that means there's going to be no pressure recovery. So what we can go ahead and say is that the pressure in area 2 is going to be equal to the pressure in area 3 up here. So we can go ahead and substitute P2, which is going to be the pressure at this constricted area right here, and for P3. So we got P1 minus P2 right here, like so. And this is looking a whole lot like Bernoulli's equation, so we can go ahead and write that up and start looking at that and seeing if we can make any magic happen. So we'll go ahead and write up the Bernoulli's equation. Alright, so I've gone ahead and written out the Bernoulli's equation right here, and we're going to do a couple of things to simplify this. First of all, that we're going to say that the change in height over here from our first position to our second position is going to be negligible. So we can go ahead and write this out as 0, cross that out. And we're also going to be ignoring our frictional heating over here, so we can also say that that is going to be 0. So we'll go ahead and cross that out. We can just go ahead and erase this and set this equal to 0 right here, like so. And we are also going to say that our volumetric flow rates, which is our A1 times V1s, the area multiplied by the velocity, is going to be the same. So we can say that A2 V2 is going to be equal to A1 V1. So we'll go ahead and write that out. Equal to A2 V2, like so. And what we can go ahead and use with this is we can go ahead and divide over both sides by A1 so that we can get V1 by itself and get an expression for V1 that we can substitute in right here. So we can say that V1 is going to be equal to A2 V2 over A1. Then we can go ahead and substitute that in right there. Go ahead and write that out. There you go. That is going to be our new expression right here. And our next step is going to be to pretty much just factor out a V2 squared over 2 right here. So we can go ahead and write that out. This is going to remain, this part right here is going to remain the same. And then we're going to factor out this V2 squared over 2 again. That is going to leave us with a this 1 minus A2 over A1 squared, right? So we will have 1 minus A2 over A1. And then this is going to be squared right here. This is going to turn into squared over squared. Go ahead and put some parentheses around that. It's going to be equal to 0. Alright, so I've gone ahead and cleared up some space over here to write with. I've left our expression for our pressure at the first location minus the pressure at the second location up here, because that is going to be important. We're going to be bringing that back in later. And the next step for our expression down here is that we know that the area of our first location, which is down here, this expanse right here, that is going to be much bigger than the area at this constriction right here, all right? Because you see it's going through a very tiny area right here, and it's gone through a very large area right here. So that we know this expression right here, this A2 over A1, this is going to be something very small over something very big, which we know is going to be pretty much 0, especially when you're squaring both terms, all right? So we can go ahead and pretty much just say that this is going to be 0, cross that out, and then this is going to turn into a 1 minus 0, which is just 1. So this is just going to turn into v2 squared over 2, since it's just getting multiplied by 1. So we can go ahead and write that out. So we'll start with our pressures. Alright, and then we can pretty much just subtract this side over here since we're looking to get an expression for our V2 here by itself. So we'll go ahead and subtract this over, and when that happens, this P2 minus P1 is going to reverse signs, so this is going to become P1 minus P2. And then the next step would be to multiply the 2 over, and then finally you would just square root everything. So we'll go ahead and do all that in one step right now. This is going to be the square root of 2p1 minus p2 all over the density of the fluid. There you go. That is going to be our expression for V2 right here. Alright, so our next step is we are going to be substituting in our expression that we saw for earlier in the video for our P1 minus P2 into our expression down here. As you can see, we have this pretty P1 minus P2. So we can go ahead and substitute all this right here in for this right here. And that is going to turn this 2/3 into a 4/3 right here because we're multiplying by 2. So we are going to have to remember to do that. So we'll go ahead and write this up over here. So we're going to have V2 is going to be equal to the square root of 4 density of the ball minus density of the fluid times dOg, and then we still have this 3 at the bottom, 3 density of the fluid. There you go. And there you have it. As you can see, this is going to be our expression right here for our V2. So we can go ahead and erase the rest of this. We are not going to need it anymore. There you go. All right, and our next step is right now we have this velocity of the fluid relating to this diameter. But what we want to get is we want to find an expression for the flow rate as it relates to the height of the ball within the cylinder. All right, so we're going to need to find a way to get this expression in terms of height, right? And pretty much a way that we can do that right here is that we know that this diameter up here, it is going to be changing as this slope expands out right here, right? So we know that as we go out, this diameter is going to be expanding out, and it's going to be expanding out based on a rate of the slope times the vertical height of this cylinder right here. This is going to be h, this is going to be the height of the cylinder, and this expression that we can use for this is going to be d is equal to do plus m, which is going to be the slope, right? The rate that this is expanding out as it expands up as well, times h, right? So this is going to give us our big diameter up here. Alright, so now we have our expression up here saying that the diameter at the top is going to be equal to the initial diameter, or the diameter of the ball, plus the slope multiplied by the height of our rotameter right here. Alright, and the next thing we are going to use is we are going to say that our volumetric flow rate, which is what we are trying to solve. We are trying to solve for our volumetric flow rate in terms of the height of the ball. And we know that the volumetric flow rate, that is going to be equal to the velocity at our second position right here multiplied by the area of our second position. All right, and we already have our V2 right here. It's this expression, but we need to find an expression for A2 so that we can get height involved, all right, because we are trying to find the flow rate in terms of height. So we'll go ahead and just leave this as V2 right now, and go ahead and do some substitutions in for A2. All right. Now we know that this A2, this is pretty much just going to be a subtraction of two concentric cylinders, right? We have a concentric cylinder up here with a diameter of big D right here, and then we have a second concentric cylinder, with our initial diameter, the diameter of the ball right here. So we know that this is just going to be our pi r squared of our big D, and we're going to subtract that by the pi r squared using our little d, our initial diameter, the diameter of the ball, and we can go ahead and write that out. So we know that this is going to be pi d squared over 4, because once again we had to substitute d over 2 in for r since we're not going to be using the radius. And this is going to be minus pi d o squared over 4, like so. This will be all in parentheses right here. All right, and next thing we can do is we can go ahead and substitute this expression in for our big diameter over here that we already solved for. So we'll go ahead and do that now. And we can go ahead and bring this 1 over 4 out into the front, as well as this pi. Since they both are involved, we can bring a pi over 4 out to the front. All right, so this is going to turn into dO squared plus 2mh plus 2DOMH, 2DOMH, and then this is going to be turning into m squared h squared right here. And then we have this minus dO squared still. That will all be in parentheses. And right here we can see that these dO squareds are going to cancel. So that's going to simplify things quite a bit for us. All right, we can continue to simplify this expression right here because we know that the slope of our rotatometer is going to be very minuscule, all right? It's almost going to be negligible. It's only going to be going up at a slight slope, a slight outward slope as you change the height. And you're also going to be squaring this. So squaring a really small number is going to make it even smaller. So this is going to be pretty much 0 right here. So we can go ahead and cancel that out and not have to worry about that. All right, and as you can see, this 2 is going to become 2 over 4, which is just going to become a 1/2. So over here, we're going to get Q equals V2 pi, then this DOMH. We gotta write their equal sign over here. DOMH all over 2. All right, and then we have our V2 right here, which we solved for earlier. And as you can see, we have this, we will substitute this in for our V2 right here. So we'll go ahead and write that out. All right, so that is our substituted V2 right here. And then on the outside, we are going to have our pi DOMH all over 2. As you can see, we're going to have this square root of 4, which we can call 2 and bring that out. That will cancel with this 2 down here. So that is going to be an easy way to simplify things up. So we'll go ahead and say that Q is equal to H. We'll go ahead and put H out at the front. H pi DOM. We can go ahead and write this down so it looks a little better since we're not going to need this over 2 anymore. H pi DOM. Then this expression once again, minus this 4 right here. All right, and there you have it. This is going to be our final expression right here. This is going to be the solution, the answer. Go ahead and circle that. We are going to be known and given pretty much everything else on here. So this is just going to be one big constant. We're going to know what the slope is, what the diameter is. All right, the only thing that wouldn't be given to you is the height right here. So this is it right here. This is how you find the volumetric flow rate in terms of the height of our rotatometer. And that is going to do it for today's video. I hope you guys enjoyed.